two strangers that we need to design that supports the tread in a stairways. So there are treads. So there is tread 1, tread 2, tread 3, and these are treads. Like there is a steps on your stairs, right? Timber treads. House. That is, let's say you have 2-story house are to be designed. So we need to design these strangers. This is a timber strangers that we need to design, right? Make sure that under bending it will not fail. The person who is walking on that one, it will not going to be fall down. So that's the main criteria. A sketch of the stair is provided below. Yep. For the imposed actions, the client has decided that 1200 1.2 meter or 1200 millimeter wide stairs should be designed to support the greater of uniformly distributed load. So you need to have a uniformly distributed load, like a live load, and you have a concentrated actions applied to the each tread. So you have a concentrated load applied. If person is standing on the treads, how it happens. Each treads and its fixing brackets weigh 35 kilograms. So if I draw these treads, this one, this is the treads, and we have these stringers like these are the stringers, and there is a threads, and there is a stringers here as well, and in between you have these threads, right? That's how you are climbing. So each thread is 35 kilograms. That's the weight of your threads. Both stringers are laterally restrained only at 75 millimeter wide barrier. So you have a lateral restraints only in here, right? So that is attached with the bearer. So that will hopping. If we need to use F14 hardwood, that we need to use. Determining a suitable size of the stringers that satisfy the strength criteria. So we need to say that how big these strangers, let's say this is B and D. Can you tell me how big I should use B and D that will be enough for house to be not broken? So if these strangers that we need to design, right? That B and D, and they already given us F14 as a hardwood. Now let's start solving these examples. I hope you have a standards open ready for you, and let's start driving into it. Now there is a we need to try something, meaning that for, let's say, for a beam, let me just put that 100%. For a beam, we will have a try L over D equal to 10. Now your first questions comes that where it's gonna come this L over D equal to 15. How do I know in the test? No, in the test you don't need to know. This is just engineering experience that you will get. Let's say you have this beam, and its beam is supported here. Let's say this is timber beam supported. So the length of that beam to the depth of that beam, if you take the non-dimensional ratio, it is just sitting about 15. That is general sense that if you do a lot of work, you will try to maintain these L over D ratio for strength and serviceability ratio. That is just a quick check that we do it. So L over D 15, that is kind of an assumptions that we will try to maintain this ratio assumptions. In the test, you don't need to worry about these ones, L over D ratio, because we will give you, or you can just try any D value. Look, D value could be any value, but you don't want to say that D equal to 1 millimeter, right? You don't want to make these 1 millimeter tiny stringers. You need to have a reasonable D value, like 100 millimeter, 150 millimeters, and so on, like the depth of your timber beam. Like I can explain you that one in here, like you want to have a reasonable timber stringers like this D, right? That's what you want to assume. You don't want to make a D like this. Look, when you do this design, you need to feel it. You need to feel it means when you get a number, you don't just blindly follow it. Okay. So let's say L length. Let me find out the length. Length over D equal to 15. Now the length we know that is 3000. Someone say that okay, this is not 3000, this is different length, but look, this is just approximate, so stay with me. That length I can say 300 millimeter, that for strangers, depth of that stringers. So you will have 3000 millimeter over 15 equal to d. So if I just quickly show it to you here, that is, let's say 3000 over 15, you will get 200. Let's say d equal to 200 millimeters. Now in that case, let's try 190 millimeter by, that is a depth, by 45 millimeters. Someone might say, where it is coming from? If you have a supplier, they will give you this catalog like a one steel. So you have this timber cross section, which we going to try 45. Of course, this is not right answer. Okay, by the way, this is not right. 190 by 45 may not work, right? It may not work, meaning we need to come back and increase the size if it is not satisfied. But this is starting point. Let's try 190 by 45, because you remember in our lectures we have straight away given us the cross section size, that you have this particular beam and you just check it whether it is adequate or not. But in here we just want to design it, that you have a accents, then you need to find it that strangers. Now let's try to find the length of the strangers. If you want to find this length of the strangers, let's copy this one and let's paste it. But I paste it. Oh, okay. Come on here. All right. So now we need to find the length of these stringers. Okay. Now if I want to find the length of these stringers, let me draw it. My question is, how much this length? How much this length? Okay, that's fine. Let's use the triangle. That this red one is this length, and let's say this length is here. This length is, I draw this one and I draw this one. Okay, and this is right angle. This one I know 3000 millimeters, right? That is given here. Now in here they have given us this 150 millimeters. You can see these 150 millimeters for the one height. Now how many of them are here? How many of them are there? That will going to help us. So you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So you have 12 threads, and each thread is 150 millimeter high. I hope you understand that. So this height that I will get 12 times 150, I get 1800 millimeter that side, right? So that height is 1200 millimeters. So if I want to find this one, I can just do the Pythagoras theorem. 1800 square. I would have 1800 square plus 3000 square. I get 3498. I get 3498 millimeters. Just take it 3500 millimeters. Right. So that is the length of the stranger. So I can just provide the details to you. We have 3000 millimeters here. We have 1800 millimeters here. We have 3500 millimeters here. I hope you're okay with that one so far. No questions, right? Now let's continue for our actions, right? We need to find what would be our load, our shear force, and our bending moment, because that is we need to find. Okay, now let's do the one strangers, because we need to first find a dead load. Let's find a dead load, and then we're going to find a live load as well. Now the dead load, this is the strangers that we are going to use. That is 45 millimeter by 150, and let me put that in the length like this, and that is 45, right? That is 190, sorry. 190. Now, if someone asks me what is the density, because to find the one, we need to find the density of F, what was that? F14 hardwood. So F14 hardwood, what would be the density? Now, if you remember that the standards that we used at the start of the semester, I can point it out that our start of the semesters, you have these 1170.1 permanent traction constructions. You have this gray iron bag, which is the hardwood. By the way, this gray iron bag is the hardwood. We have 11 kilonewton per meter cube. So then F14, this is the F grade gray iron bag, that is hardwood, and that is given in our question, that hardwood. So for that hardwood, we can say that density would be 11 kilonewton per meter cube. Where is coming from? That is coming from table number A1 of 1170.1 2002. Now that is the 11 kilonewton per meter cube density. Now let's continue that another dead load. So you have, if you want to calculate the dead load due to the this one, then the dead load will be, let's say, self weight of the stranger. Self weight of the strangers would be how much density? 11 times kilonewton per meter cube. You know the drills, that you just multiply this perpendicular area to get the UDL load, 0.045 meters. So I just multiply by this area, right, to get that red one. So 11 times 0.19 times 0.045, I get 0.09 kilonewton per meter. That is the weight of the one stringers that is applying the dead load on that stringer. Now let's talk about the self weight of the thread. This is a self weight of the stringer. Let's talk about the self weight of the thread, because these stringers need to carry the load by itself, and they need to carry the load of this thread as well. Let's say self weight of thread. So that is, each thread is 35 kilograms. And if I want to find the 35 kilograms, let's convert into Newton. 35 times 9.81, that is just the gravity of the earth, and 35 times 9.81, it gives me 343.35 Newton. And then we can just convert into kilonewtons. Let's say divide by thousands. You get, in the kilonewtons, you get 0.34 kilonewtons, right? Now we need to get it in the kilonewton per meters. In that case, we just need to multiply by that 250, because I think they are 250 meter wide. So 250 meter wide. So kilonewton per meter. So let's say UDL load is equal to 0.34 kilonewtons over that 0.25 meter wide. So 0.34 over 0.25, you get 1.36 kilonewton per meter. Now this is the weight of the one thread, sorry. Now to find the load coming on to the one stringers, because the load per stringers, then you can just divide by 2, because half will be carried by the each strangers, right? I hope you understand that, kilonewton per meter. So it's 1.36 divided by 2, you get 0.68 kilonewton per meter. If I want to explain you that you have these stringers, you have another stringers, and you have a thread in here. So the weight of the thread is 1.36 kilonewton per meter. So the half will goes here, half will goes here. So each thread will have a 0.68 kilonewton per meters UDL load, and its own weight is 0.09. So the total dead load that you're going to get is let me find that how much load that we're gonna get. Dead load on stringer due to self weight and trade. Is it called trade? Yeah, trade weight. The stringers has a weight of 0.09, has a weight of 0.09 kilonewton per meter, plus each trade weight 0.68 kilonewton per meter. So plus 0.09, you get 0.77 kilonewton per meter. So that is the 0.77 kilonewton per meter is the weight of whole systems. Weight of the whole system, meaning that these strangers will gonna get these strangers. Let me use another color. These strangers, due to his own weight and due to the trade, it will get 0.77 kilonewton per meter is the weight. Now, so that is 0.77 kilonewton per weight that they will get. Now let's find it out now, the permanent load and then design force and actions. Okay, any questions so far? Unmute yourself if you have any questions there. Any questions, by the way? We have so far calculated the dead load, which is 0.77 kilonewton per meter, that is coming on to these strangers. That is just the dead load, which is 0.77 kilonewton per meter, right? And they don't change over the life of the structures. They will be there for the whole time while your dimensions. This is design, and there is no right, there is no any magic numbers that we just tell that okay, this is the numbers and that's everyone got that. It's not a such thing. This is engineering and we need to design for worst case. Now let's continue. That you have this 0.77 one. Now let's have a live load. Let's have a live load. Let's now do the live load. Let's do the case number 1 for the live load. What is the case number 1? If you use that same standards and they did not give you the live load, but they say that it is house, I believe it is the self-contained domestic and residential, yes, and self-contained dwelling, stairs and landing in the self-contained dwellings, and you have a uniformly distributed live load is 2 kilopascals. Table 3.1 AS/NZS 1170.1. So case number 1, UDL load, live load of 2 kilopascals, that is coming from table 3.1 of AS 1170.1. all right, now that is the live load 2 kilopascals. Now in that case we want to have this combination of those live loads. Okay, now let's do that. Okay, so let's do the live load things. Okay, so let's say you have these stringers and you have a live load on this one is 2 kilopascals. We need to convert into kilonewton per meter. So you have 2 times 1.2 over 2, because per stringers you get 1.2 kilonewton per meter. 2 kilonewton per meter. Someone might say where this 1.2 coming from. That's you have this distance from one stranger to another stranger is 1.2 meters, right? That is given in our this one. So 1 will get 1.2 kilonewton per meters. Now if you get the 1.2, that is live load. Now the shear force due to the live load, let's calculate that. Let's make it a horizontal and then we convert it into the inclined one. So let's say you have horizontal. Let's say this is horizontal strain. Just don't worry about the inclined one. Don't make complex. So let's say you have this 1.2 kilonewton meters live load. 1.2 kilonewton meters live load. Now 1.2 kilonewton meter live load. What would be the reaction force? So the reaction force you will get, that is, let's say you have this 3 meters horizontal distance, because you have this 3 meters horizontal distance 3 meters, and for that 3 meter horizontal distance, if I want to calculate this point load, 1.2 times 3, 3.6. So you get 1.8 kilonewton reaction force, 1.8 kilonewton reaction force. Now, if I want to calculate the reaction, let's say shear force, let's say you want to calculate the shear force. Shear force is not our intention, just do the bending. And let's say you want to calculate the bending moment. And for UDL load, the bending moments that you get at the maximum, that is the bending moment, design bending moment, WL square over 8. W is 1.2, which is 3 square over 8. So you get 1.2 times 9 divided by 8. You get 1.35 kilonewton per meter. Right. So I think that is the design moments that is due to the first case, load case number 1, where you have 2 kilopascals load applied. So this is the design bending moment, that is the case number 1. Now there is another one that they talk about that. So what is my story? I will have different live load. Case number 1, where you have UDL load. Case number 2, where you have point load. Case number 3, I'm talking about live load. Case number 3, 2 person carrying refrigerator at stairs. So let's say there are 3 different load cases, and from each load cases I will calculate M star, and I will get the maximum M star. Worst case scenario, and then for this maximum M star I will multiply by 1.5, and I will also get the M star for this is dead load and this is live load. You with me now with the whole story? So it will come, but first of all I'm trying to figure it out who is going to dominate the design. All right, so now we continue driving on this part. We have a concentric load. So same table 3.1, domestic and residential activities, stairs. We have a concentric load 2.7 given to us. 2.7 given to us. So let's say you have these stringers, and concentric load applied to this one is 1.37 kilonewton. Someone might said, why you are putting in the middle? Because that is the worst case that we're going to get. If you put somewhere else, you will not be. So this is case number 2, where we are considering concentric live load, and the concentric live load would be how much? 2.7, sorry, 2.7 kilonewtons. And the concentric live load is 2.7 kilonewtons coming from table 3.1 AS1170.1. So if I have this the loading 1.7 sorry 2.7. Now let me calculate that moments that we need to know for 2.7. Give me a minute. I think there is an equation. I think WL to the power 4. So if I want to calculate the moment, that is the bending moment diagram, that is look like this. For this point we have, let's say this is PL on 4. let's say this length is 3 meters. So the m star for the second case would be 2.7 kilonewtons times by 3 meters over 4 meters. You get much? So 2.7 divided by 2, because we need to get it for one stringers. So 1.35. Thank you for that. So 1.35. So 1.35 times by 3 over 4, you get 1.01 kilonewton meters. That is the second m star. What was the first m star? 1.35. When you have a UDL load, live load, case number 1, you get 1.35 kilonewton meters. That is 1.35, right? Yep, 1.35. Second live load that we going to get is where is it? 1.01. So point load, point live load, and that is live load case number 2. We got 1.01 kilonewton meters. Right, so far so good. Let's continue on that one. Just give me a minute, please. All right. Now, another case that we want to investigate is there are two people carrying the refrigerator. Sorry about the drawing, but I hope it makes sense. Carrying the refrigerator, they are at a distance of 1.5 meters. I'm making it up this one, okay? And someone is just have a upstairs. They want to have a refrigerators sitting on the upstairs, and someone carrying that refrigerators for you. Let's say the one person's weight. Let's say each person is 100 kilograms. So the person 1 is 100 kilogram. Then you can just multiply by 9.81. Oops, sorry. Oh, it's disaster. Let's say times by the gravity, or 9.81 or 10. Then you have 1000 newtons divided by 1000 to get it in kilonewtons. So each person is providing 1 kilonewtons of load onto that strangers. So let's say you have someone might say you will have a 0.5 kilonewtons. Yeah, that should be work. But let's say 1 kilonewtons, and that there is a refrigerator weight as well. So let's include refrigerator weight inside. So let's say you have this situation now. There is a strangers. You have a 1 kilonewtons load. 1 kilonewtons load. You have a 1.5 apart. 3 meters total distance. So you have a 0.75. You have 0.75. In these situations, you have a reaction force 1 kilonewton here, reaction force 1 kilonewton here. You will have a shear force diagram that is 0. Shear force diagram like this, 1 kilonewton and 1 kilonewton, which is 0.75. If I want to calculate the bending moments, the bending moment diagrams would look like this. And this bending moment would be the area of that shear force, which is 1 times 0.75. So that would be 0.75 kilonewton meters. If you really want, you can just take a cut here and say that what would be the moment here. This moment would be 1 times 0.7, force times distance, right? So that moment for the load case number 3, load case number 3, we have 0.75 kilonewton meters. Now we have 3 live load case. Live load cases, I repeat again, UDL load, case number 1, UDL load, it was 3.05, let me check again, 1.35 and 101. So 1.35 kilonewton meters, this is the m star. Second, you have a point load, live load, and that is 1.01. kilonewton meter, that is limestone third live load. 2 person carrying refrigerator, you have a 0.75 kilonewton per meter, that is the M star. Right, now we need to make a decision now, engineering decision, which one is winning. Now in here, the live load, the final live load would be maximum of these three, case number 1, case number 2, and case number 3. So maximum of 1.35, 1.01, and 0.75. So 1.35 kilonewton meters. I hope you understand that. Unmute yourself if you still struggling to get that. That final live load that our strangers will experience in the worst case is 1.35 kilonewton per meter in any given conditions. Okay, so we don't need to design for this one, because if you're designing it for this one, it is automatically account this one. It will automatically, the beam will not gonna finish. So we're going to design for 1.35 kilonewton meters, right? And the dead load was how much? 0.77, I believe 0.77 kilonewton per meters. So dead load is, let's say this is a stringers, this is the dead load, 0.77 kilonewton per meters. Let's say length is 3 meters. The moment that you're going to get is WL square over 8. M star due to the dead load equal to 0.77 length 3 square over 8. So 0.77 times by 9 over 8, you get 0.87. M star due to the dead load is 0.87 kilonewton meters. So ultimate bending moment, or you can say factors, which is M star, be 1.2 G dead load plus 1.5 your live load, which is 1.2 G. G dead load is 0.87 kilonewton meters plus 1.5 times 1.35. So 1.2 times 0.87 plus 1.5 times 1.35, 3.07 kilonewton meter. So that is my final M star that I'm going to design. Now there are many arguments that is come across, that hey, this one is not account, this one is not taken into account, this should be there, this not to be removed, and so on. As I mentioned, we are work with the very worst case scenario in here that will helpful for us to design it. Okay, look, this is a very light structures. It's not be like kind of a primary structure. Of course you don't want to fail it, but at least your strangers would be safe if you have this kind of scenarios. Okay, so this is the M star. So our cross section was how much? Our cross section was 190 by 45. The capacity that MD we're going to calculate for this cross section should be greater than M star. If these things don't happen, we're going to go back and change the size, like make it bigger, right? Now, so M star we already calculate. MD should be greater than M star. That's the check we're going to make. Now that check will going to validate our initial assumptions. You remember that assumption that we make, we're going to try this one. That these assumptions that we're going to try, that need to be validated, right? Because you say that assumption we're going to try this one. Yeah, this try is not good, right? We need to make sure that 190/45 is enough. So that's what the try that I'm going to make it in this one. So MD, let's get MD first. what has happened here? Okay, come on. Okay, all right, we just need to get the another standards. Another standards meaning that you know this 171 MD is sitting here in the clause 3.2.1.1. MD equal to this one. 5. There are 5 Ks. K1, K4, K6. We discuss in the great details in our lectures. Okay, but again we're going to crack it down. FB dash Z. We have some minutes. Okay, now you remember my bending theory that someone does not know anything about the timber design, and this is the first year mechanics of solid students. He's just joined the engineering, and he wants to give it to go. Yes, it's okay for him to give it to go. Why? Because look, I can tell you the story that if you have a beam made of any materials, don't worry about materials at the moment, it can be steel, aluminum, anything, and it will be supported at some stage, and then if you apply the UDL load due to the self weight and live load, it will just going to bend, right? It will just bend. Now if you bend, if I draw this cross section here, that this cross section here, let's say this cross section here, when it's gonna bend, it will have this kind of a it will have this kind of a bending stresses. Oops, sorry. It has this kind of bending. So these need to be, and this. I hope it is makes sense. So it would be like that. And so I hope it makes sense. So so you have this kind of bending stresses, right? This is, let's say, compression, and this let's say tensions, right? So, and this is the moment applied. So the bending stress, that sigma B, let's say sigma B equal to my on I, right? If I just show it to you in here, that if you have let's say beam, any beam, okay, you have beam, right? And these beams, I'm just applying the moment, so it's gonna bend. So someone said, can you tell me the bending stress that composed at this point? And bending stress is going to be high here, bending stress could be high here. Of course, they are same bending stress here, same bending stress here, because you have uniform cross section. So it doesn't matter whether it's a positive bending stress or negative bending stress, because tension and compression. Because if you stress this one, it would be compressed, this would be extended, this would be tensions. Now someone wants to know how much bending stress that is causing by this moment, because I need to know moment. I need to know the moment of inertia, BD cube over 12, that is the resistance against the bending due to the geometry. And you need to know the y, distance y, meaning that from the neutral axis, because when you bend it, you will see the one line. You can't see the line, but you can clearly see that there is a clear zone that you have a compressions at the one end, because it's squashing your materials, and at one end it will be extending your material. So there is a clear distinguish between this one, that is called neutral axis. Above the neutral axis you have compression, below the neutral axis you have tension zone. So that is happening. And if someone asks you to find the bending stress, yes, there is an equation in mechanics of solid, that my on I. Now in our standards it's represented by FB dash, that's fine. Let's replace this bending stress by FB dash. Moment, they talk about MD, that's fine. This what is that, MD? Yes, MD. Let's put this MD and what. Now someone might say, what happened to this Z? Yes, I can get back to you. FP dash is equal to MD I over Y, that is your Z. So FB dash is equal to MD on Z. So your MD would be FD dash times Z. Yeah, that's the same equations. If you ignore all these values that is coming from timber, any materials that will have a MD equal to timber has a FB dash times Z. So let's calculate. because Z is I on Y, which is basically BD cubed on 12 if it is rectangular, over D by 2. Why D by 2? Because you have this in the middle, D by 2, because you're talking about your cross sections, and you are trying to find the bending moments here. This is the overall D. Then you are trying to find D by 2, that is the distance from the neutral axis where you want to find the bending stress. So if I just simplify that, BD cubed over 12 times 2 on D, this cancels, 6 square, so you have BD square on 6, right? That is your section modulus Z. So let's do that. Z is equal to BD square on 6. You have a B of 45 millimeters, D of 190 millimeters square, and then you have 6, right? We have, that's what we assume, I believe. What we assume is 190 by 45. Yep. So let's put that 190 square times by 45 divided by 6. You get 270,750 millimeter to the cube, right? So in that case you have this Z value, and FB dash, which is your bending stress. I think we have given, what is the designations? F timber is F14. Okay, that's fine. For F14, if you use this timber one, go to the appendix. We used table hash 3.1 last time in MGP, correct? One more table that is given here. That is table is F14, and FB dash for F14 is 36. Table hash 2.1, and that F14 is 36. Okay, page number 155, F14 36. So that is given to me, that FB dash is 36 megapascals or Newton per meter square. That is coming from table number hash 2.1. AS and ZS, sorry, AS only, no New Zealand, 1720.1, because we have F14 grade. Now let's calculate the moment MD. Of course, there are no factors at the moment. It's just the mechanics of solid students, not the third year students. FB dash is 36 megapascals bending strength times by Z value we calculated 270,750 millimeter cube. So you have 36 times 270 times 750. You get 974,700 Newton millimeters, 9.7 kilonewton meters, right? So that's the bending stress that you just get it out there without any that factors. Okay, and now we're going to driving into that that factors. Okay, so by looking at this one, I can say 9.7 is quite high, meaning that it will be 3.07. It's okay, we will do it. So without any penalties, we have this 9.7, but it's not correct. So let's driving into that 5 K1 K4, what was that, K6 K9 K12, K6 K9 K12 FB dash Z. Let's crack everyone one by one. 5. By the way, that equation is coming from close, again I can show it to you, close 3.2.1.1. let's write it down. Close 3.2.1.1. 2.1.1. Now capacity factors. Capacity factors close 2.3. Let's go there. Okay, there are two tables given to you. Table 3.1, that is for members. Table 2.2, joints. In our course we don't work on the joints, so that's no, we don't. But once you are able to read these tables, you are also in positions to read these tables in the future career if you come across this design. Now there are different grades are given. In category 1, as I mentioned, where you have a secondary members of your structures, then you have category 1. Where does this fails, then only 25 meters square of area of your home or your structures would be affected. Category number 2, when you have a primary members, the primary members fail, they will take more than 25 meters square of area. If you have a bedroom of 5 meter by 5 meters, then it is only affected that much. Use okay, category number 1. Category number 2 is the something that will have a primary members. And category number 3, like if you have a hospital, fire station, police stations, where you are designing, where you have a post disaster functions, then you have these capacity factors. Higher penalty applied here, like you can have up to 40% penalty meaning that you want to apply the safe, right? You want to use the larger cross section here, you want to use the little bit smaller cross section here. This is smallest cross section because it's not critical. So in here we are going to do the category number 1. You know the stairs, right? Stairs are not be the criticals. If the stingers fails, it will not gonna take your whole buildings down, right? So it's kind of a you can have just affected less than 25 meters square of area. So we are in category number 1. We are in the F14. All other timber and say we don't have F14 here, we don't have anything here, all other grades. So we take 5 is equal to 0.9. I hope you understand that 10% penalty is quite reasonable in the house structures. And that is coming from table number 2.1. We have a category 1, affected area less than 25 meters square. And we have also add secondary members. Primary member and secondary member, let me explain you that. Let's say you have a beam and other beams are just joining that beam, right? So those are secondary, blue one, because if they fail, just don't worry. But if this big one is a primary, if this fails, they will take everyone with them, right? So that's how you can distinguish primary and secondary, that how criticals they are in your structure. So that's 5 done. K1 K1 is I think you remember that K1 is the duration of the load factors. Look, 5 seconds, 5 minutes, 5 hours, 5 days, and 5 months, and 50 plus years. Students tell me, look, I'm designing it for 50 years. Can I take this one? No. This is the probability of your members to come in the ultimate load situation in the given conditions. Meaning that in the given conditions, one examples I give it to you, that in the ultimate conditions, we assume that live load is 2 kilopascals. What was our ultimate load? Let me explain you that in the situation. What was our critical m star value is 1.35, which is 2 kilopascals, right? It's quite high, 2 kilopascals, that Udl load. So it's meaning that in any given condition, the live load 2 kilopascals will become to your house, in any given condition, saying that you have whole stairs will be filled by the people. Any given condition in 50 years time. That is very unlikely happens, but it may happen. We don't want to say it may happen. It may happen, let's say, for 5 days. It does not mean that 5 days is that one. It's like it happens for 1 minute or 2 minutes or 3 minutes, and then after 1 or 2 years, another 1 or 2 minutes, you add up 5 days. So it's just like a probability. So this is a tables that you don't need to get confused that, oh, 5 seconds, 5 minutes, how come that you are taking 5 days? It's just a probability that your members going to come in that ultimate situations over the life of their structures. Okay, it's very unlikely, but we don't want to say that it's unlikely meaning we have 0. No, it may happen, so therefore we have some kind of 6% penalty. This table should be read in conjunction with the appendix G, and I already explained you that appendix G situations, I think in the book. Remember that appendix G1, and we are working on this 1.2G plus 1.5. We have a distributed load and such. So we are taking 0.97, let's say, for 5 hours short-term loading. Okay, so we take it 0.97, and we have a not roof load, so we have just taking 0.97. So let's say this is an assumptions duration factors. We have taken 0.97, 0.90, 0.97. Say it is a short duration, and let's say you have 5 hours, that we just assume that it may come across with that 5 hours 0.97. Now K4, because next one is K4 here, by the way. So K4, this is the called duration. What is the name of that one? Duration of load factors for the strand. So that is the name. K1 is the duration of load factors. Okay, load duration factors. Let me write it, by the way. Load duration factor, and that is coming from table 2.3 of AS1720.1. All right, K4 is, I think, seasoning and so on. So K4 here, they did not say whether it's a seasoned or unseasoned timber. Let's assume it's a seasoned timbers, right? We don't want to have someone just cut the timber and just bring it to your site. It's not going to happen. Some seasoning will be done because we are taking from suppliers. So suppliers will generally have some process done on that. So we have a seasoned timber, and generally K4 equal to 1. So seasoned timber K4 equal to 1. Let's assume it is a seasoned timber, and that is in the clause 2.4.23 of AS1720.1. And where is that? Here, seasoned timber. For seasoned timber, generally K4 equal to 1. If in case your suppliers give you the equilibrium moisture content, then you can calculate K4 value 1, take away 0.3. These suppliers will give you how much moisture presence in your timbers, the suppliers. Then you can just quickly jump in here and just substitute a value, and you can calculate the K4 value. Otherwise K4 equal to 1. K6, which is the temperature. Temperatures, K6 generally taken 1 unless you are in the Queensland North, or you are in the Darwin, north of Australia. Then you have a high temperature zone. We are taking K6 equal to 1. Let's say this timber beam has not specified anything, so no high temperature zone. So that's the no high temperature zone, K6 equal to 1. What else now? K9. K9, what is that K? This is, by the way, temperature factor. Temperature factor. This one K4, what that called? Partial seasoning factor. Partial seasoning factor. And this is temperature factors K9. What that called K9? Oh, here K9 is just how much it's going to have a combination of strength sharing. So it's called strength sharing factors. K9 is a strength sharing factors. I think there is no any such things. K9 equal to just taken 1, because I think we already done the strength sharing by ourselves. You remember that we done the calculation by ourselves, that Okay, we say that we just done the calculations for ourselves. There was no any strength sharing, so it's just one, right? Because we all the direct load, dead load was calculated for individual, so there was no any sharing that we need to take into account by K9. So let's say no strand sharing. We have taken the examples where take into account that strand sharing things, because you see in here, if you have a situation like this, you have multiple members, you have n combination member 4 and so on, you have different different situation, then you take into account this K9. Our lecture examples, we use this one, right? So you have experienced this one, but in our case this one we don't have K9 value. Now K12, last one. The last one, K12, is what we call that one. It's called stability factors, clause 3.2.4 is called stability factors, and that is coming from clause 3.2.4 AS1720.1. Now K12, so that is the K1, K4, K6, K9 and K12. So we have these stability factors that is done in this situation. Now in this way, let's calculate K12. So for the K12, you have these two factors that you need to get in rho B S1. So we have a rho B S1. Rho B, what is the rho B called? Now the rho B is called material constant, and we have F14, I believe. F14 we have seasoned timbers, we don't have unseasoned timbers, so F14 we take it 0.98 rho B. Right, so let's take rho B 0.98. Rho B 0.98, what that is called? Material constant. Where this coming from? That is coming from table number 3.1 of AS1720.1. S1, S1, what is S1 called? S1 we have called slenderness coefficient for lateral buckling under the bending. So S1 we will have a these situations, by the way, that you have a loading coming on to the beam, and your restraint, lateral restraint is at the end. You remember that. Then your LAY is 3500. You remember that, right? I can show it to you again in the questions, but you understand these figures. I think these figures is basically talking about that your beam would be laterally kicking it out, laterally torsional buckling, right? It's not about local buckling, it's about the global buckling. Global buckling means the whole members will have, along the length of the member, it will have this kind of camber, or it can have this kind of bending. To prevent this, once you put this restraint, so the distance between the restraint is represented by LAY. In our examples, they say that your beam will not be restrained for along the length of the stringers. It's just going to restrain at the end. It's written here. It's written here that both stringers are laterally restrained only bearer support. So it's just only restrained here. So we calculate this one 3500 millimeters. You remember that we calculate 3500 millimeters here. So only restraints apply at the 3500 millimeters. So LAY would be 35 coming to play, but it's moving now. Good news. All right. Now, so we have these equations that we're going to use. That we have this situation, not like this situation where the beams are loaded upward, it's going downward load. So in that case, we have this S1 1.25 dB, LAY on D 0.5. LAY is 35 because our beam is restrained at this end. So LAY is equal to 3500. So S1 equal to 1.25. You have this beam, right? And when I load it, the load situation, when your load is coming on the top of this, when I bend it, this become compression, this become tensions. So when your beam is loaded in a way that is a compression edge loading, this is a compression edge, then you use these equations. When your beam is loaded like this, when your loading are pulling this end, loading like this, pulling this end, and your tension edge, so you bend it like this, this is your tensions, right? Because look at that, I'm trying to pull this end, and that become your tension edge. Then your tension edge would be this one, that beam loaded along the tension edge. No, it does not mean that it's just sitting on. Look, I understand your concerns. Okay, now it does not mean that it's just this picture is just sitting on here. No, it is like this. It is completely, these barriers might be like this. You see, it's not just like a sitting on that one. Let me check. Only at 75 millimeter wide barriers supported. Both stringers are laterally restrained. So the full lateral is not like this and only restrained. It's full lateral restraint here. It's laterally restrained. You see what I mean? It's not like just you provide this one. So it has this full restraint here. Not like just you have these stringers and you have just sitting like this. No, it will have a full this one, otherwise it will just going to rotate, you know what I mean, from one end. Just slide that stringers on, just sitting on top of it. So you have a full restraint there. It is not laterally restrained on that end, you see. Yeah, but look, this is again engineering decisions. You can clarify with your builder how they wants to do it, but normal practice that you want to tie that end, you know what I mean. So therefore this, but of course if you think that there are cases where you want to I'm not against to use any of these cases. If it is aligned, you can check it different cases as well. But let's say for our practice, we have these kind of situations that we have it. Okay, so let's say 1.25 D is 190, because if you remember our section was 190 and 45. And then 45 LAY was 3500, and that is 190 to the power 0.5. So 190 over 45 times by 1.25 times by 3500 over 190 square. You got something wrong here. Oh, not square. 3500 divided by 190 power 0.5 times 190 over 45 times by 1.25. You get 22.7 S1. So let's do the rho B times S1, which is rho B was 0.98 times 22.7. So 22.7 times by 0.98, you get 22.2. Let's check it this one. So if you have a 22 less than 10, not here, we will be in this zone. In this zone meaning we will have a lateral torsal buckling. So K12 equal to 200 over rho B S1 square, and that is coming from the closed number 3.2.4, because rho B S1 is greater than or equal to 20, and our rho B S1 is 22.2. So 2000 over 22.2 square, sorry, 200 over 22.2 square, you get 0.41. So let's put everything together now, the whole package. MD, please write it again. MD equal to 5 K1 K4 K6. I think I'm remembering this equation by myself without looking, because I write so many times. you also need to make a practice, such that you know all your flows by heart. So, but let me find that equations. Where is it? Yep, there you go. K1, K4, K6, K9, K12, FD dash Z. 5 was 0.9. Let's put that. K1 was 0.97. K4 and K6 are 1, and K9 1, K4 1, K6 1, K9 1, K12 we just calculated 0.41. I think that is a dominant one. FB dash, I think I show you that FB dash, right? 36 megapascals. So that is 36 Newton per millimeter square megapascals times the Z value we calculated, section modulus BD square on 6. You have 270,750. 270,750 millimeter cube. 0.9, 0.97, 0.41, 36, 270, 750. So you get 3488, 743.7 Newton. Divide by 1000 Newton millimeters. So divide by 1000, you get 3.5 kilonewton meters. Just divide by 1000 two times. So let's check MD value of 3.5 kilonewton meters, which is M star. M star is 3.07. Just spot on. M star 3.07. Look, in the real world, let's put it 3.1. In the real world, I think this is very close call. Very close call, meaning that you just need to optimize a little bit, just boost up a little bit, okay? But in theory, it's okay. But on papers, on the practice, you might need to just reinvestigate, just increase the size by one size up. Look, here you have 9.7 without any these timbers, but look how much you have 9.7 kilonewton meters. How much penalty? 3.5 divided by 9.7. You get about significant reductions. About 64% penalty. About 65% penalty was coming from those things. You can see that there are more than 50% penalty from 5, K1, K4, K6, K9 and K12. all together they are applying 65, because there is your actual 9.7 kilonewton meters, but then standards don't want to take 9.7 kilonewtons. They just want to apply the 65% penalty. Biggest penalty is coming from this lateral torsional buckling, because you don't have any stringers laterally buckles. There are global buckling occurs. Anyway, any comments, any questions?